Hi there. We're just going to give it a few minutes for other people to show up. Hopefully. Do you have plans for Thanksgiving?
I'll go back to my home in Maryland to visit my parents. Yeah.
Nice. Are you going to stay there after Thanksgiving, or are you going to come back to campus?
Okay, we'll come back to campus after Thanksgiving.
Yeah,
Yeah.
that's good. Are you leaving this weekend, or are you going to leave like Tuesday or Wednesday?
Sorry?
Are you leaving this weekend, or are you going to leave like Tuesday or?
Probably like, I think I will take a flight on Saturday.
Okay.
Wait. Yep.
So you'll come to class on Monday, but from your parents' house?
Yeah, maybe.
Good. Don't forget we have a quiz on Monday.
Okay, sure. How many quizzes we have left for the semester?
3 quizzes. So we've got one for 3.1, 3.2, and 3.3.
Okay.
And I think the way that I've done it in the past is on the second to last day of classes, we'll have 2 quizzes, right? And so it's just a quiz day where people come in and they take the quizzes for 3.2 and 3.3. And then the last day of class is project presentations. So I'm trying to figure out what's the best way of doing project presentations, because we're remote. Like, it might be fun to have you guys switch the computer over to you and have you talk. You can do like what I have here, like some kind of a setup, or you can have a share screen, a presentation that you do that you write on, whatever.
Okay.
But I think it might be neat to have you guys all hear each other talk.
So I can do the PowerPoint, right?
PowerPoint's great.
Yeah, okay.
You guys will need the presentation anyway, because you're going to send it to me. You can, we'll give it one more minute before we get started. It's always easier if everybody's here. Everybody in my classes have been running late today. Like my 8 o'clock class, people kind of trickled in throughout the whole hour. And then my 9 o'clock class, I had, almost all the students show up at the very beginning, but now it seems like people are getting tired. They've got like whatever tests or quizzes or things they've got to work on. All right, so let's go ahead and get started. So we just wanted to, like I said, remind you guys that Monday we have a quiz on 3.1. Our homework is due for questions 1 through 3. This is chapter 3 now. And then we've got classwork for 3.1. So that's stuff that maybe we'll have a chance to start today. Yesterday, we were working on the lecture examples for 3.1, and we did the 2 boats. Remember, there were the boats that were, where am I? The boats that were moving, yeah. So the boats, one boat was moving south, one boat was moving due east, right? And then we calculated the distance between those 2, okay? So the distance between those 2, we found from this formula here, 4 times radical 25t squared minus 16t plus 4. I think we were also asked to come up with the rate of change of distance as a function of time. So this would be our rate of change of distance as a function of time, right? So are they moving away from each other at any given time? Are they moving away from each other? At what rate are they moving away? How fast are they moving away from each other? So let's think about how we calculate the rate of change. We're going to take the derivative of this function here. Okay, so now I'm going to rewrite this. So if my d of t, I'm going to write it as 4 times 25 t squared minus 16t plus 4, and that's raised to the 1/2 power. Okay, so when I go to take the derivative of this, okay, to find the rate of change, I'm going to do the power rule when I go to do this. So let me write that in a little color. So we're going to do power rule, and then chain rule. Okay, so power rule basically says I've got my coefficient that's hanging out there. Power rule says I'm going to bring down my exponent. I'm going to repeat my equation. It's a t. I'm going to subtract 1 from my exponents. This is going to become minus 1/2. And now I have to take the derivative of what's inside. That's my chain rule. So this is going to become 25 times 2 times t minus 16. Okay. So now what happens is I'm going to rewrite this so this looks a little bit better. So this is d prime of t. This is going to equal to 2 times 50t minus 16 all over. This is negative, so I can bring that to the other side of my dividing line, right? Which is, I can distribute the 2, so it's going to be 100t minus 32 all over square root 25t squared 16t plus 4. And this gives us our rate of change, right? Our rate of change of distance, okay? Rate at which they're moving together or moving apart. For those of you who know calculus, if we want to find out what's the maximum or the minimum distance between them, I would set this equal to 0 and solve for t. Okay, and that would give me the time at which I would get the maximum distance between them. We weren't asked to do that, so we're not going to worry about it. But just so you know, in case you're trying to tie it into calculus that you've learned before. Okay, so those are our two boats happening together. All right, so let's think. Okay, good. Okay, you guys all have that? I'm gonna turn the page. All right, so we were talking about different rules, right? And I'm gonna extend, the last rule that we talked about was the chain rule. And I'm gonna extend the chain rule to a type of differentiation called implicit differentiation. Okay, so implicit differentiation allows us to take derivatives when I have multiple variables that are happening in one equation. Or we'll say they're present. In one equation. And it allows us, it's basically an extension of the chain rule. Okay, we're going to do an example so you guys can see how that works. So, all right, so I'm looking at my example notes, my example lecture examples again. So example 10, I've got x squared plus y squared equals 1, find dy dx, and we're going to use implicit differentiation in order to solve that. Okay. So x squared plus y squared equals 1. So watch, I'm going to write it again. X squared plus y squared equals 1. Now to take the derivative, I'm going to take the derivative of each variable, right? So what I get when I do this, I'm going to go I'm taking the derivative with respect to x. Okay, that's what this means. So I'm going to go d dx of x squared plus d dx of y squared equals d dx of 1. Okay, this is my linearity where I can break it up into individual pieces. So when I take the derivative of x squared with respect to x, what I'm going to get is 2x. And you can think of this as having an invisible dx dx. Okay, so I can write that in a really light color. So this is dx dx. That's my chain rule, dx dx. Plus, when I take the derivative of y with respect to x, what I'm going to get is my power rule, 2y times dy dx. This is our chain rule. This is the implicit differentiation chain rule. Okay, and when I take the derivative of a constant term, I get 0. Okay, now our goal is to solve for dy dx. That says find the derivative of y with respect to x. So I'm going to solve this equation with respect to dy dx. Okay, so that means I'm going to subtract 2x from both sides. So I'm going to get 2y dy dx equals minus 2 times x. Now I'm going to divide both sides by 2y, which is going to give to me dy dx equals minus 2x all over 2y. The 2's are going to cancel, so I'm going to be left with minus x over y is equal to dy dx. Okay, it's an extension of the chain rule where I needed that dy dx. I took the derivative of y squared, right? But then I had to show that I was doing dy dx. Okay, and now we need that because often we're using that to help us come up with, derivatives of something that's, more complex. So we're going to use this implicit differentiation to help us. Example 11. So give me just a second here. So example 11 says, a billiard ball is shot from the exact middle of an elliptical table in the direction of 1, 1. So that means that I've got, let's just do, right, so I'm going to go 1, 2. So my ellipse, right, and I'm getting this, I'm drawing the ellipse because this is over 2, y is over 1, so my ellipse comes out like this. Okay, so here's my table. Here's my x-axis, here's my y, and we're going in the direction of 1, 1. So 1, 1 actually isn't on our ellipse, right? But it's heading in that direction. Okay, so now what's going to happen is this vector is going to intersect our table at that point right there. We need to figure out what that point is, okay? And then we're going to have to do calculus in order to figure all this stuff out. So this is like one of our applications for how we actually apply our calculus to doing, interesting shapes and stuff. Okay, so let's go ahead and get piece by piece. Okay, so the first part that we need to do is you have to look for the location of the intersection of the ball and the table. Okay, so this is, I'm looking for the intersection of, like, this right here is going to form a line with vector 1, 1, right? It's going to look like x bar. It's going through our origin, right? Because it's shot through the middle. And now arbitrarily, I set the origin at the very middle of my table, okay? Because that makes my math easier. So remember, our vector equation for this line is going to be our point 0, 0 plus t times our vector. Whoops, t times 1. Let me make that look better. Okay, so t times 1, 1, our vector. Okay, right? And now we want this to be input into equation of table. okay, our billiard table. All right, so now our table equation, I'm going to write it out as x squared over 4 plus y squared equals 1. Okay, so let's write this out in terms of x is equal to t times 1 and y is equal to t times 1. Okay, I'm going to take these and I'm going to plug them. Remember how we found our intersections? I'm going to plug them into x and y into my billiard table. Okay, so I'm going to go t squared over 4 plus t squared equals 1, right? So this becomes t squared over 4 plus t squared equals 1. So this is, I'm going to solve for t. T equals 2 all over radical 5. When I take the square root, I've got a positive and a negative, but I only want the positive aspect of that because it's heading in the positive quadrant. So t equals 2 over radical 5. So our point of intersection is equal to 2 radical 5, 2 over radical 5. Okay, so remember that. That's our first step. Okay, so now I have to find the equation of the reflected line. Okay, so find the direction of the billiard ball after it hits the wall and bounces off. So I need the equation for the the reflected line. And then part B says, what are the coordinates where it'll hit next? This is all part A. We're going to use that new line to come up with an intersection, our new intersection point. So what we need here is I need the tangent line at the point 2 over radical 5, 2 over radical 5, right? Let me draw that like this. Here's my ellipse, and here's our tangent line. I need that tangent line because I'm going to use it to help me do projections and stuff. So I need the tangent line at that particular point. So that means I have to take the derivative of my ellipse. X squared over 4 plus y squared equals 1. All right, so it's going to become, so I'm going to go 2x over 4 plus 2y dy dx equals 0. It's just kind of like what we did before, only now the equation is slightly different. So this is x over 2 plus 2y dy dx equals 0. We're going to solve for dy dx. Dy dx is going to equal to, let's see, here. So I'm going to bring over minus, this is 2y, minus x over 2. I'm going to divide by 2y. This is going to be 1 over 2y. So this is going to become dy dx is equal to minus 1/4 x over y. Okay, so I plug in my x and y. So here's my equation for my tangent line. Let's see. Or the slope, sorry, not the equation, the slope. Tangent line at point 2 over radical 5, 2 over radical 5. So I'm going to go dy dx equals minus 1/4 times 2 over radical 5 divided by 2 over radical 5. So that's equal to minus 1/4. Okay. So now to calculate a vector on the tangent line. Okay, how that goes is I say dx dx, which is equal to 1, and then dy dx, which is minus 1/4. Okay, so our vector that's on our tangent line is this, okay, which means that a vector perpendicular to the tangent line. Remember how we found this, right? We switched the x and the y, and we negated the new y, which I'm going to make positive. So I'm going to go 1/4, 1. Okay, so this 1/4, 1 is going to be a vector perpendicular to the tangent line. So it's going to go like completely perpendicular to that. Okay. That's this one right here. All right, so we're still setting up our problem. So now what we want to do is we want to project onto the orthogonal to the tangent line. So we want to project onto this perpendicular. Ready? I'm going to turn the page so I have some blank pages to work on. So we're going to project onto that vector that's perpendicular to the tangent line. So PUV equals VV times U. So what am I projecting onto it? I'm going to project my incoming vector onto my tangent line vector, the orthogonal to the tangent line. Okay, so let's write these things down. This here is our incoming vector. And then this here is our vector that's perpendicular to our tangent line. Okay, so all these numbers are coming from. All right, so I did all that work and I got the vector that I got was 5, 17, 20, 17. Okay. All right, now our reflected line. Well, so our reflected line equation, but any of the reflected line vector. Okay, remember that W, this goes back to like chapter 1, right? W equals our incoming vector minus 2 times our projected vector. So our incoming vector minus 2 times our projected vector gives us a W of 7/17 minus 23/17. I have a point of intersection that gives me a point on the line. I now have a vector on that line, so I can come up with a line for the reflection. Reflected, oops, equation of our reflected line, right? Remember this is, right? So I'm going to say this is X bar reflected equals our point of intersection plus T times our vector, that's the reflected vector. Okay. Now the question is, where does this intersect at next, right? So what am I going to do? So for part B, my next step is I have to loop back around to step 1 to find the point of intersection between our reflected line and our ellipse. Okay, so now I say my x is equal to 2 over radical 5 plus t times 7/17. my y is equal to 2 over radical 5 minus t times 23 over 17. I'm going to plug these into my ellipse. And I'm going to find the point. I'm going to solve for it. Okay. Which, let me see. Okay, so I'm going to do that. So that's going to be 2 over, sorry, you can't see what I'm doing. 2 over radical 5 squared over 4 plus, I'm sorry, I did that wrong. Yeah, I was right here. Actually, and what we can do is we can absorb this 17 into our t. So I can make this as 2 over radical 5 plus 7 times t, 2 over radical 5 minus 23 times t. So that 17, that denominator gets absorbed into there. So let me do this. I goofed because I forgot the t's on here. Okay, so watch. So this is going to be plus 7t squared. And this is going to be 2 radical 5 minus 23t squared. And that's equal to 1. And I solve for t. It's going to be a mess, right? I have to FOIL things out and then combine like terms and then solve. So I solve for t and I get t equals 0 and t equals 0.0702. This one's going to be a trivial solution, right? Because that gives me the point where I started from. Because if you think about our line, right? So we bounce off from here to here. So t equals 0 gives me where I actually started from, and I want where its next reflection is. So this is, we'll give 2 over radical 5, 2 over radical 5, point where you started from. So we're going to use point t equals 0.0702 to solve, to find out where the next intersection point is. So that means that my x is equal to 2 over radical 5 plus 7 times 0.0702, which I got 1.386. My y equals 2 over radical 5 plus, oh, sorry, minus 23.02 gave me minus 0.721. So my next point was 1.386 to minus 0.721, which kind of makes sense if you look at our, let's just turn the page and look back at our figure here, right? So this thing is going to be bouncing off down to here. So the x will be positive, the y will be negative, right? So it kind of makes sense, logistically speaking, in terms of like where we were. Okay. So this is the coordinate of our next hit, right? So the ball bounces off and it comes down here. So first it hits at 2 over radical 5, 2 over radical 5, bounces, and then it hits at 1.386, comma, minus 0.721. Okay, so that's our next hit. You can see how we can turn this into an algorithm where I could code this up, right? I'm going to have, right, each of the different stages of my algorithm are going to be here. So I need to find that one of my subroutines here is finding the intersections, right, of our vector where our trajectory is, where's the ball headed, and the ellipse. The next one is finding the equation of the reflected line. But within that, right, I can calculate what's the derivative, what's our slope at a given point. Okay, that's one subroutine. That would return our orthogonal vector. Another subroutine would be projecting. Okay, and then coming up with a reflected line vector, and then coming up with the equation for the reflected line. Right, this part right here, I just went back and I called the same subroutine again. All I did was go through and did the same process, right? So I looped back through and actually did it again. Okay, so you can imagine if you're thinking about these in terms of algorithms, how we could code them up, because I want to turn them into things, routines that I could call again and again. Okay, so that's our billiard ball. Okay. Phew, it's a lot to think about, right? All right. All right, so we have another example that I want to do, which is, where are my notes here? Okay. Shoot, I'm missing my notes here. Okay. All right. So we have another example that we want to do, which is example 12, our last example. So we want to pump gas into a large spherical balloon at a constant rate. So we're pumping it in at 8 cubic feet per minute. Does the radius of the balloon increase at a constant rate too? Okay, so let's talk about what we're doing. So this here is a measure of volume change, right? 8 cubic feet. So cubic feet per minute is a rate of change of our volume, okay? And so what we want to be able to do is thinking about what's going on. We have a sphere, right? So I've got this sphere. It's easier to model things in terms of, fairly specific geometric types, right? My balloons typically aren't spheres, but like if I can model it in a game or a program or something as a sphere, then my geometry simplifies down a lot. Okay, so let's think about our volume for a sphere is going to equal to 4/3 pi r cubed. Okay, that's just from standard geometry, right? So now if we think about what we're given, this is a volume change. So that means we have a change in volume over a change in time, which is 8 cubic feet per minute. So the words, the information that we were given on the screen on our example, help us kind of piece apart what it is we're trying to do. So the change in volume over time, and I have my volume equation here. So if I've got my volume, 3/3 pi r cubed, and I go to take the derivative. Okay, I'm going to take that derivative, which is dv dt. So I'm going to go 4/3. I'm going to do my power rule, right? This is going to be 3 times pi times r squared. Now I'm doing my radius with respect to time. I have to put in this dr dt because all I have is the change in volume over the change in time. This is like saying the change in volume over the change in time. So then I have, the change in radius with respect to the volume, and then the change in time with respect to the radius. So I can cancel all these things out and I can get dr dt. This is our chain rule that we were talking about before. Okay, so let's clean that up a little bit. So dv dt equals, the 3's cancel. I'm going to get left with 4 pi r squared dr dt, and that's equal to dv dt. But we were told that dv dt equals 8 cubic feet per minute. Okay, so that's equal to 8. I can solve for dr dt because it was asking me, does the radius of the balloon increase at a constant rate too? So let's take a look. So I'm going to solve for dr dt. So it's going to be 8 divided by 4 pi r squared. So that's going to be 2 over pi r squared equals dr dt. So what's happening here? My radius is changing as a function of r squared, right? So let's do this. R squared is in the denominator. So it's changing as a proportion of the square of the radius. So dr dt changes inversely proportional to the square of the radius, right? So it's not constant, right? When I square something, that doesn't make it a constant rate. It changes as a square of the radius, right? So you can think about my volume is getting bigger and bigger and bigger. If my volume is going at a constant rate, my radius now has to be changing, okay, in proportion to the inversely proportional to the square of the radius, okay? So anyway, it's just something to think about. We're going to come back to this example later, okay, in a later chapter. Whew. Okay, example 13 says we have position of a particle is given by this. So we've got an x and a y and a z component, okay? Our x component is 2t, our y component is, I'm sorry, x component is sine of 2t, our x component is sine of 2t, our y component is cosine of 2t, and our z component is 3 times t. Our velocity, which is what we're being asked for, our velocity is going to be the derivative of our position. So remember, velocity is our derivative of position. If my velocity is a vector, right, then my position is a vector. That means when I go to take the derivative of the position, I'm going to take the derivative of my x, put it in my x spot, take the derivative of my y, put it in my y spot, take the derivative of my z and put it in my z spot. So I'm going to break down into my components. Right, so I'm going to go, this is x of t equals sine of 2t. Y of t equals cosine of 2t, z of t equals 3t. Okay, so now when I go to take the derivatives, right? So I'm going to take the derivative of my x here, which with my chain rule is going to be 2 times the cosine of 2t. Take the derivative of my y component. I'm going to get cosine, when I take that derivative, I get a negative 2 sine of 2t. When I take the derivative of my z, I'm just going to get a 3 because that's my power rule. Okay, now I'm going to put these all back into place in my x and my y and my z position. Right, so I'll put these into place here. So my velocity equals 2 cosine of 2t minus 2 sine of 2t and 3. Okay. If we were to find the acceleration a of t is the derivative of our velocity. So I can do the same thing that I did with my to calculate velocity. I'll do that to calculate my acceleration. So my acceleration will equal to, right, I'm going to take the derivative of my x position. So I'll have 2 times 2. Derivative of cosine is minus the sine. And I'll have 2 times 2. I've got the negative. And then derivative of a constant term is equal to 0. Okay, it's still a vector, right? I started with a vector and I ended with a vector. Okay, so that's basically it for chapter 3.1. Okay, for our lecture examples and our lecture for that. What I'll do is I'll work through some sample classwork problems, okay? So you guys can have those to think about, and I'll scan in my lecture examples later on today. All right. So remember, when you do these, you only have to do a handful on each of these here. So, don't go overboard. You shouldn't spend a whole lot of time doing it, but it's enough to help you practice on what you're trying to do. So I'm going to work through some of these here. Basically doing the power rule on these. Okay. I'm gonna try some from the implicit differentiation page too, so you can see. So dy dx is what I'm doing here. So this is going to be some of these are going to require the product rule, which is okay. I could probably simplify this one, but I didn't. Okay, these are all pretty much the same. Do you guys have any questions on the stuff that we've done so far? Okay, all right, well, why don't I let you guys go early, and don't forget on Monday we've got our quiz. Okay, and then the homework is due and the classwork is due. So we just did a bunch of classwork. Like I did more probably than you need to do. I just wanted to show you some solutions. Okay, just practice it. Okay, bye guys. Have a great weekend.